Hey guys, alright, here we go, one more time. Now that's because I just finished recording a video for a linear acceleration report. So now we're doing the momentum and KE in collisions. So we can use that as a title. We report on a study of total momentum and total KE in, I don't know, is it 3 different kinds of collisions? And yeah, 3 different, or however many you did, types of collisions. And so I would say, now you don't say elastic or inelastic, you just say first we had a cart at rest. Well, let's see, we had 2 objects. Give me a minute. How do we say it? Yeah, we have 3 different types of one-dimensional collisions. And so there's like, we had 1 object moving, 1 object at rest, both objects moving. You know, I kind of think we could have done different types. And then there's and then let's think about, oh yeah, so, and we did it with a spring bumper. And let's think about it with 3 different types of collisions. Let's just get that for now. Okay. So you say, all right, first background, and you just you define momentum and KE, and make sure you need to emphasize that momentum is vector. Okay. And that since we're doing one-dimensional, so we'll say that plus is to the right and minus is to the left. And then of course you're describing kinetic energy. And then now you go into the apparatus. And you describe, you know, we have the carts. We can change the mass on the carts. We can launch them if we like. And then we have this detector that produces the T and X. And then since we need velocity vector for momentum, and simply speed, which is this fancy symbol, it just means magnitude of velocity for KE, and okay, yeah, so this, let's see, give me a minute. So this produces, we can take, we have this here, the detector. We can produce sets of data with the time for the red cart and the position for the red cart and the blue cart. And right, so this produces these tables. And so with position time data, we can produce velocity. We can calculate a velocity, and we can calculate speed. Well, it's the same thing. We just have to remember the velocity has a plus minus, a plus or a minus, and then we can calculate the momentum and the KE. And of course, there's going to be for the red, and then there's going to be a set for the blue. And then so once we did these, so the procedure is that we had whatever 3 types of collisions, 3 different kinds, and we may do 3 more, and then excuse me. And then what we did is and then let's think about this. Yeah, remember there was something about outside forces. So the only time there's an outside force is when the spring is operating. So let's think about this. I'll pause this for a moment. Okay, so I actually hit the stop button, and it probably won't even notice very much. Anyways, so we took the data, and so then we made some plots. And so if we examine plot of x, and we can see that it moves, and you can see it's a straight line, so that implies that you have there's only some sort of instantaneous acceleration, so here it's not moving. Here you have some constant positive velocity, etc. So you point out what the graph does for you. Then you say, well, look, since I know the xt data, I can produce a velocity graph. And of course, this can show negative as well, possibly. And so, we see here that's the same when it's flat. That means it's 0, and then it was positive for a while, and maybe it might go negative. And so then we can produce. Then that allows us to produce graphs of a graph of momentum and KE for the 2 carts. And I would suggest maybe you produce a sum. So now here's what's going on. Since we're saying, like, we don't know about conservation of momentum yet and conservation of kinetic energy, right? So you're producing all these graphs and you're studying the kinetic energy and the momentum. And that's now where you start saying, well, hey, let's examine our first type of collision. This, remember, there was, I guess, it's an elastic collision. And so we have momentum, and there's the red cart and the blue cart. So let's say if one cart is sitting still, so it has no momentum, and then it starts, let's say the red one's the one on the left, I don't remember, and so now it starts moving towards the blue one, and the blue one has been it's sitting still, and now the blue one, the red one hits the blue one, and so now all of a sudden the blue one is going to the right, and the red one might be going right or left. Let's just say the red one's now going to the left, and then maybe it hits the wall. You know, you have certain behaviors here, huh? So, wow, why don't we think about graphing? How about we graph? So we got the blue, and we got, the red, and we have momentum of the blue. Well, what about if we make a graph of the total momentum? What happens there? And you say, wow, look at that. It never changes. Or it does change. We discussed it. What does the P total do? And then you can define, this is, let's see, this is, say, our start right here, and this is before collision, BC, and this is after collision, and that sort of thing, huh? So now you have your types of collisions, and you have, well, what happens to the momentum, or the momentum total, and then you could do the same thing with kinetic energy. So then you can say, okay, so we're going to say that when they bounce off, it's elastic, and we notice P total and KE total do this, and we're going to say that inelastic is when they stick, and what happens when they stick? P total and KE total. And then you say, so we conclude that momentum is conserved, or kinetic energy is conserved or not conserved, that sort of thing. And yeah, and so it's pretty straightforward. We don't want to get this to be too complicated. So recall now, we never did a whole explanation of conservation of momentum or conservation of KE, because we're assuming we don't know about those things and we're discovering them. Keep that in mind. Okay, that's it. Not so bad.